Alright, welcome back everyone. Now, for this short tutorial, I'm going to provide you with one further statistics questions before I'm going to upload a full explanations on the year 2020 November further maths paper, maybe by tonight. Alright, so let's stay tuned and let's get started. Alright, here you go. This is a very lengthy questions here. Alright, now I'm going to break down this explanation into a few pieces. So we're going to look at the first one. Alright, now let's read through first the whole question before we start here. Now we have a large population consists of four species, sort of four, you can say that for data that they have already collected in this case, and then each one claims to be in the proportions of P1, P2, P3, and P4 respectively, where the sum of their proportion must be equal to 1. Now the proportions here just refer to probability. Right? Now, in order to test this claim, a random sample of size n is selected, and then the numbers of each species are found to be A, B, C, and D respectively. All these A, B, C, D are the observed frequency for the sample that have already been collected of size n in this case. Now, our first task is to show that the chi-square statistics for a goodness of fit test simplifies to this. Right, now that's our first section. Right? Now, once we have successfully obtained the chi-square expression, here we are further provided with the informations regarding the proportions for P1 and P2, P2 and P3 and P4, which are equal to each other, and the values of A, B, C, D, which are their observed frequency given as 15, 25, 39, and 21 respectively. Right? And then by denoting the common value of proportions P1 and P2 by the letter P here, we need to further simplify the first chi-square expressions into a more simplified form that is shown in the second question here. Right? Now, for this expression, we're going to determine a P naught, all right, a P naught value, in this case, the P naught here, for P, which the value of chi-square would yield minimum here, right? And then once we obtain that, they want us to use the value of P naught, which produce a minimum chi-square, in order to carry out the goodness of fit test, or which means we are going to perform the chi-square test in this case, right? At a 5% significant level. And then lastly, um, they want us to deduce that, or basically they're saying state giving your reason, the conclusions of the test for the value of P other than the P naught that we have already derived in the previous section. All right, very long, right? Okay, yeah. Okay, all right. Now let's look at the first section here. All right. Now I have prepared a table. Usually when we handle chi-square question here, it's always best to prepare a table, a table that where we can record down all the individual observed frequency, which I have already written down here as OI here. Okay. All right. Observed frequency. All right. And then we will also have the expected frequency. So we will have the expected frequency. We will have the proportions also, P1, P2, P3, and P4. Now we know that the total observed frequency must tally to n, because that is the size of the sample that we are handling in this case, right? So our next step is to obtain the expected frequency. So the expected frequency is basically NP1, NP2, and P3 and P4 here. Right. Now that shouldn't be that tough here. And then once we have done the observed frequency, we have evaluated the expected frequency. Now, all we need to do now is to evaluate the chi-square. So I'm going to write down the chi-square expression, each individual chi-square expression first. So here we have, based on the formula, we're going to write this divided by its um, expected frequency. Okay, here I think I shouldn't include the summation here. So let me erase this summation here. I should put the summation at the end here when I want to sum up all these individual expression, right? So we can repeat the same process here by having the second one here. And P2 and then C, and then after that D. All right, now these are all the individual chi-square component, and then therefore in order to calculate the chi-square here, therefore chi-square is given as such. Now I'm going to write down the formula here. Square here, I always forgot. We're going to sum up from 1 until we have okay, please ignore this, it should be 4 sets only. Okay, so from here I'm going to copy down all the expressions that I have. Now therefore I have a n p1 square Okay, now what come next is purely algebra. I think most of you would be very good at this um, algebraic manipulation here. So I'll just carry out the expansion in this case. So if I expand this, I would get a square. Here I will rearrange it directly. Okay, so here you will see that I have MP1 here, and then I will have a negative 2a here, and then plus NP1, right? That is my first one, and then my second one will be here. Try to put a bracket. That will be b square over NP2. Okay, you can see that. That will be 2b. Now that will be my second one, and then third one c square 2c now. And then lastly, I will have the last one, which is given as d square. Okay, and then there you have it. All right. Now, once you are going to arrange it in a particular order by collecting all the terms required. So here you can see that we have. All right. So we have already obtained the first part here. Right. And then next we have. And then finally we will have that okay. Now don't forget it is given that the sum of this proportion, which is actually equal to a 1 here, So I just simply write it down here. The sum of the proportion is actually equal to 1. Therefore, it means this is equal to 1. And then we know that the sum of all the observed frequency would yield an n. This part will be 2n. This part only left with n here. Therefore, our final expressions will look like this. Okay, negative 2n plus n definitely is an n here. Therefore, we managed to uh, prove the chi-square expression that represent this particular goodness of fit test. All right? So I hope that is clear at this point. All right, now stay tuned. I'm going to move on to the second section shortly. All right, so let me continue from here. 100, so I'm going to factorize this part here. I will have, okay, let me see what do I have here. I'll have 39 square here, or 0.5 minus p. And then subtract 100 here. Yeah. And then if you simplify this, you would get, I have already pre-calculated this, so it's easier for us in this case. It's 850. And then this part here would be 1962. All right, so if you simplify that, you will get 8.5 over p, 19.62 over 0.5 minus p, and then minus 100, right? So we managed to prove this second expressions of chi-square after you simplify it, right? So stay tuned for the next section shortly. All right, our next section here, we need to determine the value P naught here of the proportions P for which this value of chi-square is minimum. Now that sounds like calculus to us, or there are other ways you can actually find the minimum, of course, but for these types of functions for chi-square, it's best we apply differentiation here, right? So therefore, we're going to differentiate this in order to figure out when the chi-square will have a minimum value or maximum value. So we're going to differentiate this with respect to its proportion. Right? So if you differentiate this, you will get 8.5 p square. This one will be 19.62 square here. And then, of course, that will be gone, right? And then we will get a stationary value for chi-square when the d chi-square dp is actually equal to 0. This is where we are going to apply the conditions of stationary number to obtain the minimum value for chi-square. Right? So from here itself, you can actually simplify that. Okay, it's a huge number to simplify here, but I'm going to just rewrite that in such a way that will be 19.62 p square here, right? And then of course you can expand that. Okay, and then what we have now would be 8.5 p square, and then okay, this one require a bit of calculator. Okay, just let me finish this. Okay, let me see what do we have here. 8.5 by 0.25. Right. So I will get 2.125 here. Okay, that will be 19.62 p squared. And then by rearranging this, I will get, let me just confirm the number in case I make mistake here. So I will get 11.12 p squared plus 8.5 p, and then after that minus 2.125 equal to 0 there. All right. Okay, so from here, you can factorize it or you can solve for the value for p here. So we managed to get two value of p here. Just let me algebra here. I have already pre-calculated the value, I think. Okay, let me see whether I got the value itself. Yes, correct. So if you solve these quadratic equations, you will end up with both negative 0.9 963 and 0.198 here. Okay, and then there you have it. These are the value for P, but we know that for this setting here, probability must be equal to a positive value. Therefore, we're going to conclude that because the probability must be greater than or equal to 0 here. Right. Now, of course, at this point in time, how do I know that whether this is a minimum or maximum then? Right. Now, there are many ways we can actually do this. Right. One easy way that I always practice, okay, or that I always use would be a line number. So I'll just draw a line number here, and then all I need to do is just place all my roots that I have already obtained here. So 0.963 and then 0.198 here. Okay, this is P. So, all right. Now, what I'm trying to analyze here is what is the value for the gradient for the chi-square in this case, or the derivative for chi-square. Okay, we can try to substitute a value 0 in between here, okay, into the p's. So if I put 0 into the p, I will get a positive number here. Yeah, I'll get a positive number here. And then you can try putting another sets of value here. All right. Most probably you are going to get like if you try 0.5 for instance, sorry, we cannot try 0.5 here. We can try like 0.4 for instance. Okay, so if you try 0.4 here, we are going to check whether we are going to get a positive number or a negative. All right, so for sure here you will get a negative number here because we are interested in the value of 0.198. So we don't really need to evaluate this, right? And then at this point, how does a line graph actually help us to determine whether this chi-square value is minimum or maximum? All right, now if you look at this, this one is actually positive. Let me check whether I did that correctly. Just let me check the value one more time. Is this is 0? Oops, sorry, I think I made a mistake. We should not substitute a 0 inside here because it will be undefined. So maybe like 0.1 inside here. Okay, so if we put 0.1 here, it will be, oops, sorry, that's my mistake. You should get a negative itself. So let me correct that. You should get a negative. Here you should get a positive instead. Right? You can always check that out. Just let me check that very quickly. Okay, 0.5. Let's try to use negative 0.1 then. Okay, negative 0.1. Okay, so 0. Okay, there's 800, so negative there. So 0.1, 0.4. Yes, correct. It's a negative. Therefore, this is the sign that we're getting. And then you can see that this is actually going down. From here is negative, and then when we reach the stationary point is a 0, and then this part here is positive, so it's going up. Therefore, this nature of the stationary point is a minimum. Therefore, you can actually verify that chi-square is minimum uh, at p not equal to 0.198. All right, and then there you have it. That's how we determine the um, minimum value for chi-square. Of course, some of you prefer to proceed further with the second derivative of the differentiations. By all means, you can go ahead, right? So stay tuned for the next section. All right, this is our next section of the question here. All right, okay. Now let's look at this. Carry out uh, goodness of fit test at a 5% significant level with p equal to p naught here, right? And then thereafter we're going to state giving your reason the conclusion of the test for the value of p other than p naught that we have already found. Just to recap again, the p naught value which yield the minimum chi-square that we have already obtained is 0.198. All right. Now we're going to use this value to calculate the chi-square test statistics. All right. Okay. Now to perform goodness of fit using chi-square here, we're going to write down. Um, Typically, we're going to write down our hypothesis statement. All right. So our hypothesis statements, our null hypothesis, and our alternative hypothesis in this case. All right. Okay. Now for testing goodness of fit, usually the null hypothesis will be given here, right? Or you could actually write this down as it fit in the distributions or the proportions correctly, right? So it's or you can mention that or a good fit to the distribution. Oops, sorry. Good fit with the to the distributions with p equal to p naught, right? You can also mention that, right? And then whereby for the alternative hypothesis, it's either you can omit it or you can write it down because the chi-square test for null hypothesis, the alternative is always opposite of it, right? So just for formality, we write down not, right? Or you can say that it's not a good fit to the distributions with proportions of p not equal to p naught, right? Okay, so I hope that is clear at this point, right? Okay, now once you have set up your hypothesis statements, all right, now we're going to go through the same stage here, which we're going to carry out our test statistics. So for our test statistics, we're going to calculate our sample chi-square. So our sample chi-square can be calculated using this value here, sorry, this formula here. Knowing that the p naught that we have already found out is this, right? So we're going to substitute this into here. All right, and then I have already done the pre-calculations here. We would use 7.896 here. Right, now this one will be our test statistics chi-square value, right, that we have obtained from the data that we have collected from our sample, right? Now, next, in order to help us to make a conclusion as to whether we're going to accept the null or reject the null in this case, we're going to refer to the critical value of 5%. Right? Now, before that, for the critical value, so I'm going to write it down here, the critical, the critical value. We're going to obtain this from MF 19. All right. Now, before that, we need to know what is the critical value that we are looking at. Right. So here I'm going to just simply draw the distributions here. All right. Now, I think this is a chi-square. I keep on drawing the normal distribution. All right. Chi-square shape usually looks something like this. All right. Now, for 5% significant level, so what that means is this area, which we known as the rejection zone, right? So this is rejection region, consists of 5%. Right? Now, on your or in your data booklet, MF19, there, the data booklet will give us the area for this region here. Now, because we want to find the 5% significant level, right, so therefore this region would be 95%. So in order to get the critical value, we have to refer to 95% on the data booklet MF19. And then at the same time for chi-square, we will have to have the degree of freedom in this case. So the degree of freedom, I'm going to write it down here. I just use V to represent degree of freedom. Degree of freedom is basically the sample size minus 1 for this case here. Right, we have like 4 sets of data, so therefore 4 minus 1 here, which will yield a 3. Okay, now it's time for us to refer to the data booklet. All right, now we are looking at the data booklet for in MF19, looking at the sections chi-square distributions. Right, now if you recall previously, our degree of freedom is 3, and then the percentage that we are supposed to look for in this data booklet is 95%. So we look under 95% degree of freedom, which is 3. Okay, so underneath this, it will give us the critical value. As I mentioned before, the rejection zone is 5% here, but your MF19 show this shaded region, which is 95%. All right, so I hope that is clear. We're going to bring this value back to our calculations that we have done previously. All right, so the value is 7.815. Now we're going to compare this critical value. So here I'm going to label it C. We're going to compare this critical chi-square value with our sample chi-square value that we have already calculated here. Now, based on this, we can conclude that this critical, sorry, this test statistics chi-square actually fall in the rejection region. So if you look at this part here is 7.815 is our critical chi-square, whereby our test statistics is 7.896, which actually fall in the rejection region. Therefore, we have sufficient evidence to reject. So therefore, our conclusions will be we're going to reject H naught. Right now, by rejecting H naught here, we are directly saying that this is not a good fit with the proportions P equal to P naught here. Right? So therefore, I just make it short here. I'll say that the proportions of P is not equal to 0.198 here. All right. Okay. Or you can conclude it as the result provide us with a sufficient or significant evidence to reject the null hypothesis. Therefore, the proportions of the population is not equal to 0.198 there, right? Now, reason, okay, because our test statistics is much more greater than the critical value that we have already obtained from MF19 here, right? So I hope that is clear for this section here. All right. Okay. Now for the last section, right? State and giving your reason the conclusion of the test for the value of p other than the p naught that we have already obtained previously, right? So here I like to write down again the p naught is 0.198. Okay. Now I'm going to rewrite my chi-square value again based on this p naught. Okay, by subtracting, hold on, I think I wrote it down wrongly. It's supposed to be minus 100 here. Right, by substitute this value into the p here, we have already calculated this as 896 just now. And then bear in mind, with this value, p naught would actually produce minimum value of chi-square. Minimum value of chi-square. So therefore, this value that we have already obtained is the minimum value for the p naught that we have already found, 0.19. Therefore, it means that for other value of p here, for any other value of p in this case, it will not yield a minimum chi-square value anymore. So most probably it's going to yield any value that is larger than that. So for any other value of p, this I will call this a minimum here so it's easier to refer. And then I'll just put down for any other value of p, the test statistics chi-square value would definitely be greater than the minimum chi-square value that we have already predetermined based on the p naught 0.19 there. Now because of that, therefore the chi-square value for any other value of p here must be greater than the critical chi-square value that we have already obtained from the MF19, which is found as 7.815 here, right? Because this is already minimum, and then the minimum value exceed this. Okay, you can see that because the minimum value of the chi-square has already exceed 7.815. Therefore, we can always conclude that or decide to reject H naught. Therefore, we're going to reject H naught for any value of p other than p naught. All right. So the evidence is there. Right? This part would actually give us the supporting evidence to always be able to conclude that we're going to reject the null hypothesis, knowing that the proportion is not equal to 0.198. All right. Now, I hope that is clear for this question here. All right. Okay. Now, I hope that this would be useful revisions for your upcoming exam tomorrow. All right. Now, I will try to upload another paper or two for your revisions in a short duration of time. Right. So stay tuned, and then I'll see you again.